Okay, so I'm going to go over the MIPS architecture, instructions, and so on. Actually, this whole class is about a MIPS architecture, to be honest. Right now we're going to go over MIPS instructions. And one thing I can say is even if you don't kind of gather all this in this video, kind of bookmark it, because we're going to be coming back to this. Like, you're going to need to understand this all through the class, especially when we start going over the data path. Understanding a MIPS instruction is going to be very important, and a lot of the concepts we're going to go over, like addressing modes and how many bits in the address and that it's byte addressable, these are going to be things that you're going to need to know. So even if they don't quite sink in now, maybe come back to this later. So anyway, our whole class is going to be based on the MIPS architecture. And there are applications of MIPS processors. Granted, ARM is actually much more popular now. So MIPS is not a popular language or instruction set architecture, but it is used in Nintendo. Some set-top boxes, workstations, and the like. Most notably, SGI and Nintendo 64 are based on MIPS. And MIPS is used to control some spacecraft built at APL. Use MIPS. The one on the left actually is New Horizons, and it just a year ago made it to Pluto. But it was controlled with MIPS, and then the Van Allen probes. So that's just some quick. Notably, though, it was designed by the author of our book, which could explain why our book uses MIPS. So Hennessy developed MIPS. Okay, so one thing, we've talked a little bit about RISC and CISC, and MIPS is RISC, Reduced Instruction Set Computer. It's simple. It has fixed machine instructions, so all the instructions are 32 bits. So that's something you need to remember. The instruction itself is 32 bits. And if you go in your book, you can look in Appendix A, and page A50 is where the description starts. And we'll go over that table on page A50, but then starting on A51, all the instructions are described, and it describes how the 32 bits are split up. So each instruction has a number of fields, but add them all together, and it's 32 bits. So a 32-bit instruction is, 32 ones and zeros that describe what it wants the data path to do, or what it wants the computer to do. And one of the next things we're going to look at in this class is a data path, like how it takes those 32 bits and interprets them and does something with them. So all of them are 32 bits. Here is something very RISC-like. Only load and store instructions can reference memory. So we have data memory, where we store things. We have registers, which we'll talk about, but then there's also main memory that we can put some data in. And to get data into the data path so the instructions can do something with it, you have to get it out of memory, or you might want to save it. But the only instructions here that can reference memory are load and store. So we have things like load word, store word, load half word, store half word, load byte, store byte. So in this class, we're going to mostly deal with load word and store word. So those are the only ones that can reference memory. So load takes data out of memory and puts it in the register file. Store takes data out of the register file and puts it in memory. The addresses are 32 bits. And we use pipelining, which I think is coming up in Module 6. But we're going to talk about several data paths, but the one that is implemented the most is pipelining, a pipelined MIPS. We're going to talk about the 3 formats for machine instructions and 4 addressing modes. That's coming up also in this, and that the registers itself are 32 bits. So we're going to go through this, but you have your central processing unit, and you have data actually stored on the CPU in the registers. And we're going to have, an arithmetic logic unit and so on that's going to actually do the work. And then we have a memory out here. So there's a number of registers. And then obviously load word and store word gets data in from memory into the registers, and store word takes it out. But these registers here are also 32 bits. And a word is 32 bits. So here's a prettier version of what I just talked about. So we're going to have the control unit, CPU, and we are going to talk about this in Module 4. We have the register file and we have the memory, and again load word or load and store. We're going to mostly talk about load word and store word. The only way to get stuff back and forth is with those. And then not so much we're going to talk about floating point ops and system management and input and output. Actually, we're not going to really talk about these much at all. We talked a second ago about MIPS registers. So the CPU does all its calculations using data from registers. The MIPS instruction set architecture we talked about has 32 registers, and each are 32 bits wide. Registers have names and numbers, and actually if you look at, there's a green card in your book, the MIPS reference data. In the bottom right corner there's the list of names and register names and numbers. So you'll see on there that register 16, number 16 is also known as S0. So in an instruction you can either put $S0 or $16. The register numbers are encoded on 5-bit fields. If you look on page A51, that's where all the instruction formats start in your book, and you'll see even the first one in there is add, and there's 3 register fields, RS, RT, RD, and those 5-bit fields are the register numbers. So if you were to wanted to encode register 16, that would be in 5 bits would be 10000. That would be the 5 bits in that field for register 16. There's a couple special registers. Register 0, $0 always has a value of 0, so here's an example. Adding 0 to 2 and putting it in 3 is the same as putting the value that's in 2 right now into register 3. So, and then register 1 is a scratch pad register. Point there is don't use register 1. Again, you can find this information on that green card in your book, and then this is material more from your 204 class or your computer organization class. But these T registers So register 8 to 15 are these temporary registers, T0 to T7. They're not preserved cross-function calls, which actually is not something we're going to be concerned with in this class. S0 to S7 are registers 16 to 23, and T8 and T9 are 24 and 25. So these, if you're doing like an add or arithmetic and logic instructions, or even loading and storing, you're going to put it into these T or S registers. Okay, now we're going to go over MIPS instruction types. And again, if this doesn't quite sink in now, try to remember to come back to this, because in a couple weeks we're going to look at the data path in Module 4. And we are going to see how the data path, the circuits in the data path are set up to execute these different kinds of instructions, and how they go through a different part of the path depending on what kind of instruction they are. So an R type gets all the data from the registers, all the data it needs from the registers. So an example of R type, and again, all the instructions are listed started on A51. Their format. So R type might be an add. So if we add this would be the destination, and then one source and two source. So this says add the contents of S1 to the contents of S2 and put it in register S0. So R type has 3 registers. An I type of instruction is going to add the value that you actually give in the instruction to a value in a register, or not add, but do an operation with a value from a register and an actual value that you give in the instruction and put it in a register. So I type is also called immediate. Oops. And it contains a literal. So a version of this would be add I. So we're going to say here, add the hexadecimal value 11 to the value in S1 and put it in S0. So this is actually, this field in the instruction is 16 bits, so you're adding a 16-bit number to the 32-bit number in S1 and putting it in S0. And again, you can find one of these. Add immediate is on page A51, and there's others in there. Anything that you see that says immediate. Jump is actually a simple one, and that's on page A63 in your book. But you're just going to say jump, and you're just going to give an address. And it's actually a 26-bit address, but you can give a value. And it would be an instruction address. So you're just going to give. And so that this just says jump to this address in memory. So all the R format instructions have this setup here. The first 6 bits, remember these are 32 bits of your instruction. First 6 bits, the upper 6. So again, this is, when we talk about this is a 32-bit instruction, and this would be the least significant bit. And this is the most significant bit. And then we also might call this, these are the upper 6 bits. So the most significant 6 bits are something called an opcode. The next 5 bits, so the opcode is going to, it is an indication to the data path what to do with that, and we'll go over some opcodes. But the data path is going to read these 6 bits so it gets an idea what has to be done. The next 5 bits are going to describe the source register, RS. So in this case, register 17. Another source register, because with R-type we have 3 registers, and then the destination. This is shift amount, which is only applicable for some instructions. So there are instructions called shift left and shift right. And so that's just going to take a number and move it to the left or right. And then this is the function code. So this is another. So 0 means, a 0 opcodes means this is an R-type. And then down here, this is going to tell it which R-type instruction it is. So an add would put a 32 in that field. And if you also, starting on page 851, there's all the instructions, and it'll give you the function code. And also, if you look on page 850, there's a table, which we're going to go over. But all the way on the left in that table are all the opcodes. And you'll see the R-type is all 0. And then there's a little arrow if you look at opcode 0 at the very top. There's an arrow going to the right, and it goes to that function code part of the table. And then it'll give you all the numbers for function code. So SLT, I can't read, they're tiny. But anyway, there's all the different R types are there on that table on page 850. So here's how add S1 to S2 and put it in T0 would be set up. And of course, this is the assembly language. And this is the machine code. And because there's so many annoyances in this class, they're kind of in a slightly different order here. So there's 3 instructions that use this shift amount field. Shift left logical. And if we look on that little table, that has the function code 0. Shift right logical. Function code is 2. And shift right arithmetic. Function code 3. But this, so what a shift left logical is, it takes a number. So if this is a 4-bit number right here, shift left is going to shift it to the left and fill with 0 bits. So if we shift left 2, it's going to be 1100. So we'll shift it this way, and these shift out, and then add zeros. So shift right is going to go, if we shifted that right, 2, it's going to be 0, 1, and these will shift out and fill with 0. And then shift right arithmetic, if we shifted this right too, we would fill with the most significant bit. In this case, this is the most significant bit, and it's a 1. Immediate instructions, or I format, can have 2 registers and an actual value. And that value can be up to 16 bits. So its value can be up to -2 to the 15th to 2 to the 15th. And we'll look at the different kinds of instructions that can be used by add-I, or add-I in immediate format. So one immediate format instruction, arithmetic, is add-I. As we just said, I gave this example earlier, but we're going to take this value, which would be put into this field, add it to S1, which would be put here, and put it in S0, which would be put here, and the opcode for that, for add-I, if we look on our handy-dandy table, opcode would be 8. So the first we can look at it as a branch instruction. And if we look on page, again, A50 will tell us BEQ is a branch on equal. Branch on equal is going to see if the value in this register is equal to the value in that register. And if it is, it's going to add this offset that's given in this field to the current program counter. And the opcode for that is 4. We see that on that table. So that's how this offset is used in a branch instruction. So the third kind of format we have is J-type. And so if we're doing a jump would have an opcode of 2, and we would just give it an address here in this field, 26-bit address, and it would take that address, multiply it by 4, and go to that address. So here's a summary of the MIPS instructions. So arithmetic, add, subtract, multiply, divide. And again, all of these can be found in your book starting on page A51, and they're in alphabetical order. Well, kind of. First they give all the arithmetic and logic instructions in alphabetical order, then all the comparison in alphabetical order, then all the branch in alphabetical order, then some jumps, I don't know, so and then all the loads and all the stores. So it's not the best setup, but they're all there if you want to go find them. So arithmetic, logical, and or exclusive or, shift left, shift right, NOR. Data transfer, again, load and store are the only ones, so this is going to transfer to and from memory. From memory to registers. Load is going to go from memory to a register, and store is going to go from registers to memory. Load a word, load a half word, a byte. Okay. Conditional branch, branch on equal, branch on not equal, branch on less than, and so on. Unconditional branch. B and J actually have the same effect. Not sure why there's two separate ones. Comparison, set on less than immediate. Again, that uses the immediate kind of addressing. Set on less than unsigned, and we'll talk about signed and unsigned. Maybe we already did. Anyway. Hey, this is a repeat. Register mode is where operands are in register, so that's the R type. Immediate mode is where there's a literal in the instruction that we use. Base relative, we take the contents of the base register and an offset to give the memory address. So that would be, we're going to go over that a little more, but a load word so here we're going to go to the address in register S2. We're going to add this 3 to it. So that's the offset. And that's the register, that's the address where we're going to load the contents of S0. So this is base relative. Okay, so that's how that works. So this is load word, load the contents of S0 into the address given in register S2. plus 3 bytes. This is in bytes. PC relative, we give a displacement, multiply it by 4, and add it to the program counter. So multiplying something by 4 is the same as shifting left 2. So we take a value, so here's a value 2. If we shift it to the left 2, it becomes this. So now it becomes 8. So if we shift something left 2, we're multiplying it by 4, and we're going to see that in our data path. But another thing we have to remember here, so these instruction addresses are the address of a byte. Our data and instruction memory are byte addressable. Okay, so address we're given is the address of a byte. But a instruction is a word, 4 bytes, 32 bits. So we can see this displacement would be the number of instructions we want to displace, but to actually turn it into a number of bytes, to change it to the correct address, we have to multiply it by 4 to turn it from words to bytes. And remember throughout the class that these addresses, both instructions or data, are the address of a byte. So a lot of times we're going to need, a word always has to start on a byte divisible by 4. So a word is going to have to start at byte 0, byte 4, byte 8, and so on. But one word in memory will take up bytes 0, 1, 2, 3. So when we're doing arithmetic or load, store, or branch, those 16-bit values need to be 32 bits. So we sign extend it. So that means whatever is in the most significant bit, or that bit, the highest bit in the 16 bits, is just repeated out to 32 bits. If it's a logical instruction like and or, we just put zeros in those upper 16 bits. But this is how we turn from 16 to 32. 1, we extend whatever sign is in the most significant bit, and then this one we just add zeros in front of the 16 bits. So this is what the instructions look like. Immediate, we have the 2 registers and the value. So one of the, so anything with an I on the end. Register addressing looks like this. It's an R type. So we have an opcode and a function code and 3 register values. Base addressing, this is for load and store. And you can see load and store starting on page A66. The description of how to turn it from assembly language into machine instructions. So there's an offset here in this 16 bytes, and you're going to add it. So the register is going to contain the address, and then you're going to add to that this immediate value. And that's the address where you're going to either load a value into or get a value from. PC relative, we're going to take this value in the 16 bits, add it to the current program counter, and that's going to be where we go. And pseudo direct is we're just giving you the address, and you're going to go there. So this is part of that table I was telling you about on page A50. This is the opcode. That's the first upper 6 bits. If the opcode is 0, it's going to have this function code in the lowest 6 bits. So these are all the R-type instructions and their function code. And then an opcode of 2 So the opcode, when the opcode is 0, the operation is determined by the function code. When the opcode is 1, the operation is determined by the RT field. And that's branch on less than 0, branch on greater than 0, and such. We actually aren't going to talk about this much in this class. But what you do need to know about is an opcode of 0 and the function codes, because these are all R-type, and we're definitely going to look a lot at R-type instructions. All right, and we're going to repeat that here, that in this, only the load and store instructions can access memory. Makes it fast. Registers are fast to access, so we're just going to do all of our loading and storing, and then our arithmetic is going to be done on register values or immediate values.